In this exercise, we're going to use a PID controller to control a mixing tank. This mixing tank doesn't have a reaction, but instead we assume a concentration coming in, and we're going to control the concentration coming out. The concentration of fluid coming in can be anywhere from 0 to 2 molar. We have a volume of 100 cubic meters. Sorry about that. And an inlet flow rate of 100 cubic meters per hour. We're going to do a species balance with the normal amount, so the change in moles inside is going to be equal to the number of moles in minus the number of moles out plus generation minus consumption. Since we can measure this in concentration, if we just normalize by the volume, since it's constant, we have our concentration depending on the concentration in and the volume flow rate in, and the concentration out and the volume flow rate out. So we're going to set our set point to 1.5. Our set point is going to be 1.5 molar initially, and then down to 1 molar. Our maximum feed concentration, as I mentioned before, is 2 moles per liter, and the minimum is 0 moles per liter. So we'll report the PID tuner parameters, and then show time plots of our dynamic response of our controller. So first we have our parameters that we've been told in the problem. We'll actually code these now. The first is that our concentration initially is 0, our feed temperature is 300, and our time interval is 10 minutes, and we'll just go ahead and do 100 time points between those 10 minutes. We'll initialize our storage arrays. We'll have CA, which is going to be zeros, and CA1 is going to be CA0, which is actually 0 anyway. Then CAF is going to be zeros as well. Our error, but CAF will be controlled by us. Our error is going to be zeros as well, and we have set points that starts at 1.5 and then goes to 1. We have our we have our PID tuning parameters. Let's discuss these just for a moment. The dynamics of our system are such that in minus out is going to be some function right here. So really what this depends on is this function from 0 to 2, and that will affect the whole system. Concentration out is the same as the concentration inside. So the only variable we have that we're manipulating is its concentration in. Because of that, so we can get these constants from a number of places. Let's go ahead and just didn't want to do that. Let's just go ahead and set them equal to 1 and then discuss that in just a moment. We'll discuss tuning after this, actually. But the concept is we can go, at least for now, a good place to start is our FOPDT, and make an FOPDT with a step change, look at how that does, and use some IMC correlations. So let's go ahead. Our error is going to be our set point minus the concentration at any point in time. Our integral is going to be the integral at the previous point, or just our integral variable, plus the error times the differential temperature, or the differential time, excuse me. Our derivative is just going to be the difference between the last two values divided by time. And then our feed concentration is going to be the concentration of feed at the initial time, that's our U bias, plus Kc times the error, plus Kc divided by tau I times the integral, minus Kc times tau I times the derivative. Notice this is the derivative of our process variable. If it were the derivative of our error, then it would be positive down below. But we do the derivative of the process variable, so we don't have any sharp discontinuities. So we'll go ahead then. We implement it, and then we implement it on the simulation by setting it equal to, within this anonymous function within ODE 45, where we set our variables, set our time span, and our CA0. Let's go ahead and we'll look at it. I'll go ahead and run it. And you'll notice there's no real response here to to that downturn afterwards. So we have too much Kc, I'd say. The other thing is too much tau I. So we want to make tau I larger because it will have less of an effect. So we'll go ahead and try running it again. The concept here is that we're tuning now. We're looking at the output, how it performs, and so we want this concentration to go down because we want the concentration to be near this set point. So let's go ahead and set tau I to something like 5. I'll run it again. First, let's make sure that this is even working right. Because it was just seconding down. Either way, oh yeah, that's the other thing. Our tau D is too high. Okay, I was worried for a second. Our tau D, if we have it too high, will steer us away from the derivative by just not letting us have derivatives. So I saw it in our answer. Either way, the point is more that we understand how this PID equation works. You can see we are manipulating this inlet concentration so that our red line tracks our set point. And you see that we get there. It'd be nice if we got there earlier, but this is a good start. So in the next modules, we'll talk about how we actually set these systems up to tune them so that they run optimally for our system. Thanks for hanging around.